Hello everyone, I am Alvia Tolkuril. I am going to present our work titled Cure Enabling RF Energy Harvesting Using Cell-Free Massive MIMO UAVs assisted by RIS. The authors are myself, Dr. Muhammad Y. Salim and Dr. Muhammad Ashikur Rahman. To give an overview of the presentation, I will first provide some introductory information, then I will discuss our contributions, then I will provide some background information, then I will introduce our framework. Finally, I will discuss the evaluation and experimentation, and I will conclude with discussion and future plan. It is estimated that more than 50 billion Internet of Things IoT devices are connected to the Internet. Major portion of the IoT ecosystem is transportable. The charging of these IoT nodes is a crucial factor for the continuous operability of these devices. Although the rechargeable batteries can work as a conventional power source, they can only last for a specific time interval, and afterwards these batteries will also require charging or even displacement. The great visionary Nikola Tesla first proposed to transmit energy into free space and convert the energy into usable direct current power. Later, that foresight led to the development of state-of-the-art power supply techniques like wireless power transfer (WPT) and energy harvesting (EH). The cutting edge of the wireless power delivery is the harvesting of energy from radio frequency RF signals. As the massive multiple input multiple output MIMO technique has the ability to focus the received signal with very narrow beams, it is considered for EH. To resolve the inter-cell interference issue and serve all the devices in a coherent manner, cell-free MIMOs, which is CFM MIMO, is considered for the APs distributed over the coverage area. As for our contribution of this work, we designed and implemented CURE, a novel framework for improved radio frequency energy harvesting with the combined benefit of CFM MIMO, unmanned aerial vehicle as access points which are assisted by the reconfigurable intelligent surfaces. The verification of the framework's performance is done by comparing it with the max-min fairness algorithm with respect to the spectral efficiency and harvested energy. There is an analysis done of 3 different deployment strategies for the RISs, and we made empirical comparisons between them to find out the optimal strategy. So CFM MIMO systems comprise a large number of distributed low-cost and low-power access point antennas connected to a network controller. It offers high spectral efficiency through spatial multiplexing of a large number of devices on the same time frequency resource. RIS is a relaying metasurface controlled with integrated electronics. The elements can independently provide some changes towards phase, frequency, amplitude, or even polarization. Finally, because of the strong line of sight and flexible deployments of unmanned aerial vehicles, they have been becoming capable for assisting terrestrial wireless networks. Let's talk about our framework. Here, the UAVs mounted with CFM MIMO act as the access points (AP). We consider that the UAVs are tethered with a direct energy source, so they hover at a point for acting as the AP. They also have an immediate link with the core network, which is the base station. They provide direct RF signals to the IoT devices. On the other hand, for enhancing the energy harvesting in the downlink and for providing signals to the non-line of sight locations in the coverage area, RISs are utilized. They reflect the RF signal intelligently towards the IoT devices. The combined RF signal from the APs and the RSs are harvested at the user end. Then this power is leveraged for the uplink information transfer from the user devices to the access points. Depending on the location, the uplink signal can be sent directly to either the base station or the UAV or AP or via the RS panel. The right figure presents the RS assisted energy harvesting. Here, we evaluate the performance of the framework by comparing the empirical cumulative distribution function of individual spectral efficiency per user achieved by the regular MMF mechanism and the RIS assisted MMF mechanism. The RIS assisted MMF is achieving higher amount of spectral efficiency compared to the standard MMF. For coherent linear signal, the distribution is more skewed than the non-coherent non-linear signal. The upper tail of the curve represents the users with good channel conditions, who achieves higher spectral efficiency than the other users because of the operational saturation region.
These figures represent the comparison of performance between the MMF and proposed Cure framework with respect to the harvested energy. It is evident from the figures that Cure achieves substantially more harvested energy than MMF for both coherent linear and non-coherent nonlinear energy transmission. So now, to get a concrete idea about the improvement, we increase the number of RISs leveraged for both of the types of signals. It is observed that the improvement is exponential with the increased number of RISs. We also experiment with varying number of elements in the RISs. It is seen that for 9 APs, the amount of harvested energy is very low, even with higher number of meta elements in each of the 9 RISs. There is an upward trend in case of 16 APs. A more steep curve is observed in case of 16 RISs. We also vary the number of antennas in the APs. It is seen that large number of RSS doesn't have that much impact compared to the varying number of APs.
We additionally experimented with 3 deployment strategies for the RISs and found that the hybrid strategy incurs the highest amount of harvested energy. So we presented a comprehensive RFEH framework with CFM MIMO, UVs, and RISs. The empirical evaluation validates our framework's performance. We also discovered the best RIS deployment strategy. In our future work, we will optimize the deployment for both UVs and RISs. Thank you for listening to my presentation.